Hello everyone, welcome for this session. Today we are going to get a relation between sequence components of phase and line voltages in star connected system. Let's understand first what is this and then we are going to solve it. Okay. So relation between sequence components of a phase and line voltages in star connection. Remember this is in star connection. Okay. So recall once in star current remains the same, that is line current will be equal to phase current, but line voltage is not equal to your phase voltage. This we remember, right? So what is then VL equal to root 3 times of VP, right? So this you remember. This we need to express in terms of sequence components, that is phase voltage if we speak of phase. Okay, phase voltage if we speak, this is we are going to take as VA, VB and VC, right? So VA, VB and VC are their phase voltages. This you can write in terms of phase voltages in terms of symmetrical components, that is sequence components, like VA, VB equal to VA, VB, VC is equal to 1 1 1 1 A square A 1 A square into VA naught, VA1, VA2, that is zero sequence, positive sequence and negative sequence. This you know, right? You can write in other terms, that is if you know phase voltages, you can find out this symmetrical components, that is zero sequence, positive sequence and negative sequence, that is equal to 1 divided by 3 into 1 1 1 1 A square 1 A square A into phase voltages VA, VB and VC. This we know, right? This is about phase voltages. Phase voltages in terms of symmetrical component in terms of phase voltages. Now, but in star, these two are not same. Line voltage and phase voltages are not same. Then what we have to do for that is, first we need to take line voltages. We'll indicate it as VA, VB and VC. Remember, small abc are our phase voltages, capital ABC are your line voltages. Okay, we'll take and then we'll write. Okay, so line voltages, this is equal to same formula for this also. Okay, 1 1 1 1 A square A 1 A square. This and this one is capital VA naught, VA1 and VA2. Okay, zero sequence, positive sequence and negative sequence. Only thing is this is phase and this is line in star. Now we need to get the relationship between this and this one, that is VA naught is what about in terms of phase. Okay, zero sequence line voltage is equal to zero sequence phase voltages. What is the relationship between these two, that we need to get. Similarly, what is VA1 in terms of small VA1? So this is what is VA2, this is VA2. What is in terms of this? This is, remember, it is a line voltage zero sequence, line voltage positive sequence, line voltage negative sequence, which is equal to, okay, phase voltage zero sequence, phase voltage of positive sequence, phase voltage of negative sequence. This we have to get. Okay, I hope you have got what we are going to do today. Okay, so let's express first one, line voltages in terms of phase voltages. Consider three phase star connection, which is of balanced one. If it is A, it will be B, it will be C sequence, right? This is a VA phase voltage, VB phase voltage, VC is also phase voltage. Now let's get its line voltages. Line voltages between this is vectorical. Okay, addition of this one is your VAB. Okay, remember it is vectorical addition VBC. Okay, VAB, BC and this one is CA, it is VCA, right? Now we need to express this one in terms of this one. VAB is your line voltage, VBC is a line voltage, VCA is also line voltage. Okay, VA, VB, VC are your phase voltages. Okay, this you remember, these are our phase voltages. These are your line voltages. Okay, now we'll get, for that we'll take a direction like this. Okay, now we'll apply each one of this. Okay, for this loop, calculate what is VAB is equal to. What is VAB? VAB is equal to direction you observe. This direction is in this way. Okay, so observe the direction, just move through this loop. Okay, what is VAB equal to? VAB is this plus this. Okay, just go back this direction, taking direction, and this direction is opposite, so we'll take minus VA. These two same direction, so plus VB. This can be written as VB minus VA. Okay, next, to get VBC, okay, to get VBC is equal to, apply this loop. VBC is equal to minus VB plus VC. So we can write this one as VC minus VB. So similarly, VCA. So VCA is equal to, apply VCA is equal to minus VC. Okay, opposite direction, right? At this opposite direction. So minus VC and plus VA. Therefore, it will be VA minus VC. Okay. Will represent, observe here, it is a VAB, right? This is a VAB. Will represent VAB as which term is not there, means which sequence is not there, C is not there, no? So we'll take this, we'll represent this one as capital V, capital C. Okay, this is a VC, just opposite vertex we are going to represent. So VAB is equal to VC. This is a line voltage. Okay, and then VBC is nothing but your VA, capital A. BC are there, A component is not there, so we are going to represent opposite vertex name. Okay, just a representation purpose. So this is VCA, which is not there, B is not there, so it is represented as VB. Now you can say VAB, VBC, VC are your line voltages, or VC, VA, VB, VC are your line voltages. Therefore, you can represent this one. VAB is nothing but your VC, okay, with the capital letters, and the next VBC is capital VA, VCA is VB. So these are your line voltages, VA, VB and VC. Okay, you should know what is VA. VA is VBC. Okay, VBC is equal to what? VC minus VB. Right? This is line voltage in terms of phase voltages. This you remember. Okay, phase voltages VA, VB and VC. As you know,